Now, what is a black hole? A black hole is something where the gravity is so strong that no mass or electromagnetic radiation can pass from it. Okay, it's a dead end. It's like a cliff from where everything will fall. Okay, so this thing is an opposite to the single atom, but the singular atom is said to be the core of the black hole. Okay, so whichever gave life is enough to destroy as well. Okay, so it's just that. Now, let's talk about the evolution of lithosphere. Now this is the Big Bang theory. There was a single atom, it exploded, the galaxies were formed, okay, the whole of the universe formed, and then there are lots of galaxies, and the galaxies are getting further and further apart from each other because the universe is going on expanding. You see, from below to top, okay. You see this diagram from below to top. Okay, so now we have the galaxies formed. Okay, inside the galaxies there are the sun and everything. Now let's do the evolution of lithosphere. Okay, so when we are doing the evolution of lithosphere, I want you all to first to remember our Earth looked like an asteroid. Okay, it looked like an asteroid, very rocky surface with hydrogen and helium gas. Okay, that's all. So it looks just like here in the diagram. Okay, like an asteroid. Now from here to the modern Earth. Okay, how our Earth was formed. So we'll do that. So that's why the heading of the chapter, origin and evolution of Earth, right? So let's do evolution of lithosphere with time. Okay, it took a lot of time. Okay, 13.7 billion years ago the Big Bang theory happened. After 3 lakh years ago the atoms used to form, and it took a lot of time, billions of time, and then there was a suddenly very increase in pressure, okay, giving a increase in density, and then the increase in temperature. Because of course, if the asteroid is formed and it is there and it is very compact, okay, solid matter, the density increases, the temperature also increases. So what happened here is all of the matter that was mixed, okay, all of the matters that were mixed, okay, whatever the matter the energy created, all of it was mixed. It started to separate according to its weight. It started to separate from each other according to its weight. The heavier objects, like for example, the iron, they started to move towards the core of the earth. The lighter objects started to move towards the crust of the earth, the upper portion. And we can see it now also, okay. So when you touch your land, it's mostly a rock, okay, a rock or a very soil or sand, right, on the upper part of the earth, right, on the crust. And when you go down, okay, it's a coal and iron ore and all we find there, okay. And the core is molten because the iron and all, and with the increasing temperature, everything melts, right? So this is the something. So now all the matter they started to separate from each other, and then there was a drop in temperature, okay, and it all solidified more. So now our Earth is being formed. Not the current Earth, it is being formed. Okay, it's not ready yet. Why it isn't ready yet? Because of because the atmosphere hasn't been evolved. So atmosphere is very much important. Okay. So our Earth is kind of like a ready. All of the crust and the mantle and upper mantle and core, it's kind of nearly being fixed. Okay, everything is in layer now. Now let's talk about the atmosphere. Now there was an evolution of atmosphere. Previously, our atmosphere was just comprised of hydrogen, helium, and dust particles. Okay, but now what happened when the interior of the Earth started to becoming very hot? Okay, it had to give out the lava. It had to give out the lava. There was no place to store it. Of course, right? Still now we have this volcanic eruption. So there was a lot of volcanic eruption, and whenever there is a volcanic eruption, it gives out carbon dioxide, methane, ammonia, nitrogen, and a very important and a strange thing, that is the water vapor. Okay, just like you have in the diagram, it says acid rain, but back then the acid rain or whatever rain. Okay, the rain was only needed. Okay, so when the water vapor was given out from the volcanic eruption from the interior of the earth, the magma started to come out, and the water vapor started to come out. It went and mixed around with the primordial gas, okay, from the atmosphere which was back then. This led to a drop of temperature because carbon dioxide mixed with the rainwater, okay, mixed with the water vapor, and that's how and the rainwater, and that's how there is an acid rain. But still, the temperature dropped, right? Even if there is an acid rain, the temperature dropped. Now, And when the temperature dropped, some part of the earth started to become very cold and they formed glaciers. Some parts, okay, became some parts started to receive a lot of rainfall and all. And here, thus, the oceans were created, the seas were created, okay, and such was created. And plus, when the oceans and the seas were created, they started to form a very small plants that lived in under the water, okay, and the photosynthesis started to take place. Now the photosynthesis process is taking carbon dioxide, okay, the plant processes, respiratory processes taking carbon dioxide and give out oxygen. So now the oxygen is being also formed. So this all gave to the current earth, okay, that we all live in. Now there's the other thing in your chapter, that is the evolution of life. Okay, I hope I don't have to do this. From unicellular organism, we moved to something like a fish in the ocean, and then we started to have some lakes, and then we lived in the land, and then there was this ape. Okay, and then we became bipolar, that is moving in two lakes, and then the modern human being. Okay, I hope you can do this. Okay, the Darwin theory of evolution. So evolution of life is also there in your second chapter. So just go through it in your book. Okay. And then we have the interior of the earth. This is the third chapter. Okay. And the chapter name is interior of the earth. So before going to the interior of the earth, we just saw how an earth was created. Okay. Now our earth is ready. Okay, we are living there. Now we want to study what is in the interior of the earth. Now our earth radius is 6,370 kilometers. Okay, that's the radius. If you want to know the diameter, multiply it by 2. Okay, so that's the radius that we all know of. Now we want to study the interior of the earth. So how will we study that? What are the sources? How is that possible? So there are the two sources. One is the direct source and one is the indirect source. In the direct source, we have the mining, volcanic eruption, surface rock, deep ocean drilling. Okay, and in the indirect, we have the gravitational, magnetic, seismic, temperature, pressure, and density. So let's start with the direct source then. Okay. Now we want to know what is inside our earth. What will we do? We are already mining, right? We are already going to the coal mine and the gold mine. Now it is somewhat fit deeper into the earth's core, okay, into the interior of the earth. So we do that. We go there, we check in, okay, and then we study there. Okay, we do a lot of study. We study the minerals, we study the temperature and the pressure. We see how hot inside it is in a coal mine. Okay, coal mines are very hot. Now we see the differences in the temperature, and we all do this. Now this is how mining helps as a direct source for learning the interior of the earth. Okay. Now second is a volcanic eruption. Why? Because volcano brings out everything from the interior of the earth. The magma that turns into lava was there inside the earth, from the interior of the earth. It brings out all the gases and rocks and minerals. If minerals are found, then all the lavas. Okay, so we can study that directly because it just came from interior of the earth, right? It's clever on our point. So this is the second point. Then we have the surface rock. This is how we kind of assume. Okay, we study the surface rock and then we assume that maybe the interior of the earth is kind of like a similar because everything was built in the same way. We just did how an earth was created, right? So we now know, at least have an idea that how the interior of the earth is. Okay, we will study the surface rock, and then we have the deep ocean drilling. Okay, so then we have the deep ocean drilling. Now we drill. Okay, we drill into the oceanic floor. We drill at the land. Okay, and we take out all the petroleums and all. Okay, so this we get a slight idea from here. If you want to study it, we kind of get the temperature inside, the pressure inside. Okay, so we get a kind of like a picture of the interior of the earth. Now the deepest drill is at Koala in Arctic Ocean. Okay, that reaches up to 12-kilometer depth. That's the deepest. And your gold mine, that is the deepest, is in Ghana. Okay, that is around 3 to 4 kilometer deep. Okay, so this is some of the fact. And then we have the indirect source. So first we have the temperature. So naturally, we all know the normal lapse rate, right? 6.5 degrees Celsius after each kilometer. Our temperature drops above. So we we can assume it what's the formula beneath that, beneath the sea level. Okay, so temperature increases when you go down, right? So this is how we study, and even the pressure increases and density increases as well. Okay, so this is an indirect source and assumption. Okay, and assumptions are near to correct. And then we have a very important things now. Okay, then we have the gravitational study. Now we see that gravity are different in different places. Okay, but that doesn't mean that there is no gravity at certain places. There is nothing as such. We are all guided by gravity, but then there is a slight difference on that. Okay, we see that the equators have less gravity because they have more mass. Why? Because our Earth is spheroid in shape. It is thicker in the equator and thinner at the poles. So at the thicker part, that is the equator, we are quite far from the core, right? And that is why the gravity here is kind of little less. Okay, not that less, but little less. Okay, that we won't even feel. And at the poles, the gravity is high, and this is called a gravitational anomaly. Okay, that is the difference in distribution of mass material on Earth's surface. Okay, that is called what? A gravitational anomaly. Okay, and then we have a magnetic study. Now we study Earth acts as a huge magnet. Okay, so we study about this magnetic fields and everything that goes around with it. Okay, so magnetic surveys, it provides information about the distribution of magnetic material in the crystal portion and thus provide information about the distribution of materials in the past. Okay. So now the very first question that arises is why does our Earth act as a magnetic field? Okay, so for this we don't have a very clear answer till now, but we have something called dynamo theory. Okay, in science we have something called a dynamo theory, and it suggests that wherever a source of energy is at the core, that place, okay, wherever a source of energy acts as a core, that place naturally acts as a magnet. Okay, so whatever has a core, and the core is very warm and very dense and very high pressurized, okay, that whole place naturally acts as a magnet. Okay, so this is one of the theory we got. So somehow we are getting a study of the interior. That means the interior of the Earth has a high pressure, high temperature, high density. Okay, and the very important thing now, that is the seismic activity. Okay, now what is the seismic activity? Those are the study of interiors of the Earth, the movements on Earth's mantle or plates. Okay, so that is called the seismic activity. So movement on Earth's mantle or plates. Okay, so the study of seismic movement is called seismology. Okay, and the instrument is seismograph. Okay, and when we feel the seismic activity, we call it earthquake. Okay, so there is a slight difference on the terms, right? But we usually use it as a synonym, but geographers should know it. Okay, the slight difference on the these three. Okay, so what is an earthquake then? So when we feel the tremor from interior of the earth, from the movement, okay, from the mantle movement or the plates movement, we feel a certain tremor, and that is called an earthquake. Okay, so the earthquake starts at the mantle portion, and from where it starts at the mantle at the interior of the earth is called focus, and the straight point on where the earthquake waves first hit on the surface of the land is called an earthquake epicenter. That is usually just above the focus. Okay, because that's the first place where the earthquake waves will hit. Okay, just if you don't if you are confused with this, draw this diagram and keep on going making circle. Okay, circle of equal radius. Okay, keep on going making circle, increase the radius by 2, draw, increase it by 2 and draw. Go on with that and you will see that the above surface, okay, the earthquake waves will hit the surface just above the focus. Okay, and that is called the epicenter. Now, when we are talking about earthquake, it's very important to know about the earthquake waves. Okay, now earthquake, we feel earthquake because of the earthquake waves. Okay, now what are waves? Now, for everything you need a wave. For sound, you need a wave. There are sound waves. Okay, there is no sound at the space because there is no air. Okay, because everything needs to vibrate and then your sound will travel. Okay, so vibration is important. Vibration on the molecules or the matters are important. So waves act as a such way. Waves act equally such way. Okay, the earthquake waves, they act in the same way. there are vibration, and the vibration goes on. Okay, it carries on. The molecules keeps on getting vibrated at a certain rate. Okay, and then it will travel from one place to the other, and it will decrease with the distance. Okay, we all know that. The earthquake that we felt in Nepal in 2015, the South Indian people, they didn't feel it. Okay, but we felt it. It was tremendous. So this is something, and that wave. Okay, the earthquake waves are divided into three parts. Those are the primary waves, secondary waves, and your surface waves. Okay. Now your primary waves are the fastest wave, and this is very destructive too. Okay, they travel from solid, liquid, and gas. And these are the longitudinal waves, which I'll explain you, and they are compressional waves. And then we have secondary waves. Which travels through solid only. Okay, the frequency is high, and it is transverse in nature. Okay, the primary waves is called P waves, and the secondary waves is called H waves. So in diagram, if you get P and H, please don't be confused. And then you have surface waves, which is L waves. When some waves touches the surface and moves along the surface, that is called a surface wave, which is very weak. It doesn't affect much. Okay, but the primary wave is very destructive. So a few points. Okay, so earthquake takes place in the lithosphere. Okay, depth up to 200 kilometer. Okay, mantle portion, crust portion, and here we have the transverse and the longitudinal wave. So longitudinal wave or the compressional wave is of primary wave, and the transverse wave is of secondary wave. Let's just see this. The transverse wave spends a lot of time and energy while moving in this portion, while making this crest and trough. Okay, while moving up and down, it loses a lot of energy here. Okay, so that's why it is very weak. And the longitudinal wave, also known as a compressional wave, this is a primary wave, right? This acts like a spring. It will move to a certain point, it will compress, and then it will move to another point at a much more higher level. It will again compress, and then it will move to a much more higher speed. Okay, because when you compress a spring and just leave it, won't it go further at a larger speed? That's how this works. Okay, and this is very destructive. This is the reason why. And it will move through solid, liquid, and gas, because this is just so speed, and its velocity is so high. Okay, this can just move through anything. It will be like a mad bull, right? So it will just compress and then pull, compress and leave, compress and leave. Okay, and this is a secondary wave which will waste its time, waste its energy while moving like a typical wave. Okay, while up and down, like making a throw and crest, throw and crest, throw and crest. Okay, so this will lose a lot of energy and time. Okay, so these are the two things. So, and before doing this, I want you all to remember this. Now, what is a reflection or what is a refraction? When you look at a mirror, you get your own reflection. Light torch in the mirror, okay, at a certain angle, not a very straight angle, at a certain angle, and the light will be reflected back. Okay, the light will be reflected back. This is a reflection. But light or torch on a water surface, okay, on a water surface, it will go down, but it will change its angle. So this difference in the angle between the light in the gas, okay, because you are light in the atmosphere, maybe, okay, because you are above, okay, you are in the air, and light in the water is known as the angle of refraction, and this is called a refraction. This point here, this difference, okay, this is called a refraction. Now the thing here to remember is that when a certain light or a certain wave, when it changes its nature, like when it moves from solid to liquid or from gas to liquid, it will change its angle and it will become a refraction. Okay, it will become a refraction. Now, interior of the earth, the secondary waves, as we saw, it will only move through solid, right? It will only move through solid. Now, before doing this, if you all remember, we have divided earth into solid, liquid, and gas. Okay, not upper mantle, crust, and anything. Okay, just to make it simple, this is the solid, liquid, and then solid. Okay, solid, liquid, and solid. Okay, solid, liquid, and solid. We have divided earth's interior into solid, liquid, and solid. So here, there's a difference on the matter. Okay, so the secondary wave, they only pass through the solid region, they do not come to the liquid part. But the primary waves, it comes to the solid part, then it enters the liquid part, and when it enters, it is getting refracted and the speed is getting increased. Okay, it is becoming very violent now. So it gets refracted, then again it moves towards the solid. Okay, then again it gets refracted, and this is how destructive a primary wave can be. Okay, hope you'll remember this diagram that I did in the class. Okay, so reflection and refraction. And then we have the fourth chapter. Okay, now we finished our third chapter and I didn't even know. So before ending the third chapter, just remember the seismograph. Okay, when we come to know about the earthquake history, the instrument is known as seismograph. Okay, now if they ask for the scale, okay, there is a two kind of scale. One is the Richter scale and the Mercalli scale. Okay, that's to measure the earthquake. Okay, measure the magnitude of the intensity of the shock. Okay, so if they are asking for the scale, just remember to answer Richter scale and Mercalli scale. This can be very confusing. Okay, the instrument is seismograph. Scale is Richter scale and Mercalli scale. Okay, never be confused on this. And then we have the fourth chapter. That is the distribution of oceans and continents. Now here. We did the interior of the earth, we saw how the earth was created. Now the evolution, okay, we'll study the evolution of continents and how our earth is placed like of now. Okay, so there's always been this theory that our earth was never like this. Okay, it changed from one thing to the other and then the others. Okay, so they believe that all of the continental parts, they were once one. Okay, that was known as a Pangaea. Okay, and then it changed into Gondwana and Laurasia. Okay, it started to get divided. If you are saying it started to get divided, it is moving apart from each other, all the continents. Just check here, and then this is our current continents. Okay, so there was always this belief that our continents were always moving. Okay, so this is the continental drift theory. And we have this two kind of a study to know that. One is the pre-war and the post-war. Now pre-war means what? Pre-war is before the First World War, 1915, before 1915. Okay, so we'll start with the pre-war. Okay, so before 1915, before the First World War, there was a person called Alfred Wegener. Okay, now he suggested some of the ideas why he believed that the continental is moving. He said that how continental is moving, because just check on the fossils. The fossils of mesopods that we saw here on South America, okay, we saw the same fossil on Africa. Okay, and so he came, the fossils of some dinosaurs that we saw here, we saw the same dinosaur at Africa. So he said that the fossils are all the same. Okay, now it cannot be that all of the animals, they swim and they fly. No, it cannot be. Some animals, they cannot swim, some animals, they cannot fly. So how is this possible that this fossil is found in Africa as well? It's possible only if all of the land was together. Okay. Now the other factor he gave is the jigsaw puzzle. Just like how the South America and the Africa, they kind of like, it seems like they will mix with each other, they will mix with each other, they'll fit on each other. Okay. So he gave this theory as well. He gave this example, not a theory. And then he gave this pressure movement. What is a pressure? I'll do that. Okay. If you all see in the history channels and all, people, they gather here in this river with some instrument and then they collect golds. Now where do the golds come from? The golds come from the interior of the earth that is directly opening towards the river or something. Okay, river or stream. Now that river or stream, it brings along with it the minerals along with it, and people gather here to collect it. Okay, so this is called a pressure movement. When some mineral is being placed from one place to the other, it is being pressure. Okay. Now the same pressure was seen in Brazil area. Okay, the Brazilian plateau. Now if you all see, the plateaus are the most ancient landform. Okay, now in India the ancient landform is Peninsula Plateau. Okay, so the plateaus were always there. So plateaus which were always there, with time, whatever the rock or the minerals they had, due to higher time, the density will be higher, the temperature will be higher, and all of the interior of the whatever the rocks were there, it by now it will be mixed, it will be converted into some minerals. Okay, so plateaus are always rich of minerals. So in this placement we saw that the Brazilian plateau is just a cover, while the Ghana plateau they create all the gold deposit. Okay, so naturally, if Brazil has a plateau, there should be some gold mines or something, right? Some minerals inside them, but no, they got only the cover. While the interior of the earth, that was the gold mine. Okay, the gold region. Okay, the gold rich region. The Ghana took it. Okay, because this was because of the separation of the earth, of the continents. And apart from this, there's something called the tillet. Now, till is something that is a glacier deposit. Okay, and then we found that some part of now we don't see any glacier now in Africa, right? Do we see it? Do we see any glacier in Peninsula Plateau of India? No, we do not see it. But we see some glacier deposits, some deposits that only glacier would have that deposited. Okay, just like how a river brings its sediment, glacier brings sediments as well and deposits it. So we see such kind of a deposit now. Okay, so but that's not the question. That's not a big issue here. Glacier deposits are there, it's there. Okay, that's not the issue. But what is there? What we see is the glacier deposits of Brazil and Africa are the same. The glacier deposits of Indian Peninsula Plateau and some part, okay, like Australia are the same. So we see that. So that means what? All of the part was one, and then the glacier formation was formed and the deposits were formed. Okay, and back then when it separated, the glacier was melted and the deposits stayed. And after this we have the distribution, we did that, and then we see the forces. Now we said, why did the continental movement take place? Why did the continents move from apart from each other? He said the pole fling force, that is the rotation. And because of the rotation, he believes that it took a lot of time, but the continent started to move, okay, away from the pole fleeing force. Just like most of the matter is towards the equator, okay, and not towards the pole. The same way, all gathered around the equator and not the pole. That's why pole flying away, running away from pole, okay. And then the other reason he gave was the tidal force. Just like there's high tide and low tide, okay, by the sun and the moon, okay. Sometimes in the river there is a high tide and sometimes there is a low tide. He said that maybe interior of the earth the same effect happens because of the gravity of the sun and the moon, and as because it is a solid, it cannot react so suddenly, just like a water. So it may have taken time, but the movement may have taken place because of that. Okay, so he gave that. So these were the two forces he gave. Now let's go to the post-war. Now let's go to the post-war theory, of theories. Now there was a person called Arthur Holmes in 1950. Now he believed in the continental drift theory, but he gave a slight difference on the reason, on the forces that make the drifting. Okay, the forces that made the movement of the continents. Okay, he said that it is not a pole fleeing force or a tidal force, it is the convectional current theory or a convectional force. Okay, and what is a convection now? Let's do it. A convection is now this is the diagram to explain you better. So here, okay, the one A, okay, the A, it is heated, maybe, just take for example, here is a burner and the air is being heated. It moves upward, walks to a certain point, gets cooled down, it will move down, and again it will take its place. So this cycle will carry on. Okay, the hot air will rise, it will move to a certain point, it will get cooled down, it will drop down, and again take its place. Okay, so this process is called a convection. This process is called a convection. This cycle is called a convection. Where do we see convection? We see it in our water vapor to precipitation process. Okay, this is the same cycle. There is a water vapor. Okay, evaporation takes place, forms clouds. Okay, moves to a certain point, gets cooled down, condenses. Okay, then there is precipitation. Then again it comes back to its same place. Okay, so convection. This is the same theory as convection. So he believes that there is a convection current theory. Now what is a current? When there is a difference in the temperature, okay, when there is a difference in the temperature of a higher part will try, okay, the higher temperature part will try to go towards the lower temperature zone, okay, and that will create some kind of a movement, and that movement is called a current. Happens in seas and rivers and all, okay, there are lots of current, and without current, how can you boat, right? So it happens in seas and oceans. So this kind of current is formed. So this process, along with the current that formed, okay, because from the higher temperature zone to move into a lower temperature zone, some kind of a movement is being formed that made the differences. Okay, that made some thermal differences in the mantle that led to the movement of the continuous. Okay, that's what he said, and that is called a convectional current theory. Now, to make it something that you can write in your book, okay, generated. Now, convectional current theory is generated due to radioactive element causing thermal differences in mantle portion. Okay, that's what you will write in your book in your questions if it comes. Okay, generated due to radioactive element causing thermal differences in mantle portion. Now, of course, there is some thermal differences. That's why there is a movement, because temperature from a higher temperature zone, it will move to a lower temperature zone. Okay, whatever it is, whatever matter it is, solid, liquid, or gas. Okay, so this will create some kind of movement. This will create some kind of current. Okay, there's this differences, and this is why the continental plates, there is a continental movement. We haven't come to plates right yet. Okay, now we have something called the ocean floor configuration. Now, configuration is what? When you all buy a book, when you all buy a laptop or anything mobile and all, you will get a configuration. Okay, the configuration is what all softwares are there, what all it is made out of. Now, the ocean floor is made out of continental margin, abyssal plain, and mid-oceanic ridge that you have the diagram of here. Now, your continental margin comprises of the continental shelf, okay, the beaches, okay, where you go and relax. Then you have the slope, and then you have continental rise. Okay, if you all can just go through here. So continental shelf, slope, and rise. Okay, till up till here. So if you are seeing this, okay, this is the place till where you all are allowed to swim. Okay, generally, if you are not scuba divers and all, this is the place till where you all are allowed to swim in a beach area. Okay, because after this the sea starts to get very deep. Okay, increase in distance with the beach area. Okay, increase in distance with the self, the sea starts to become, or the depth of the sea starts to increase. Okay, so always remember this. So up till this point, until the continental rise, this is the continental margin, this portion. Okay, and then from continental margin till the mid ridge, you have the abyssal plains. Okay, this is called to be an abyssal plain, and then you have a mid-oceanic ridge. Now, mid-oceanic ridge are plateaus, chain of mountains. Okay, intense volcanic zone. Now we will do what is a mid-oceanic ridge. Now, mid-oceanic ridge is a single range, the highest range, okay, the largest range of a single mountain, and that is inside the ocean. Okay, that is the ocean, and these ridges are very prone to volcanic eruption. Okay, so this ridge, this line, it is a single range of mountain, a single mountain, and that is inside the ocean. Okay, so this is called a mid-oceanic ridge. Continuously. Now, how is this ridge formed? If I have the diagram for that. Okay, I don't have a diagram for that. So these are the mid-oceanic ridge, and these are the volcanic zones. So these are volcanoes. Okay, so this is where the volcanic eruption takes place. This volcanic eruption, okay, the magma is given out. It will move to a certain distance. It will get cooled down, and it will stay here. Now the same process will go on and on and on. Okay, and here the there is a very rough kind of a landmass here. Okay, it's plateaus. It is so because the accumulation is so high, it may form some mountains. Okay, and this is how this huge mid-oceanic ridge is created. A single range of mountain is being created because of the same thing, accumulation of magma, and the same process again and again for this billion of years, million of years. Okay, it created a huge mountain range. Okay, not very hard, very simple. Now there is other reason too why the volcanic eruption takes place at such a high rate in the oceans. Now, if you will see that, the upper part, okay, the crust part is also said to be a sail, and just under the sail you have the cyma. Take for example, this brown part is a sail, and this is your cyma. Okay, and in continental zones, this sail is always present. Okay, the sail and the cyma is always present, but in ocean the sail is missing and there is only cyma. Okay, now sail is your bottle opening. Okay, it is like your cap, bottle cap. So when you are in ocean, you are in Saima, you don't have a bottle cap, so of course whatever inside, it will come out naturally. Why do you cap your bottle? So that you don't want your liquid, you don't want your water to just spill out, right? But here in ocean, there is no sail, there is no cap. So naturally, whatever is inside, it will get spilled out. Okay, so this is one simple reason. And then I said you all right to do this homework, and nobody showed me. I want your homework, huh? So this is a mid-oceanic ridge, okay, the blue part, the mid-oceanic ridge that we did here, okay. Now the red parts are your small volcanic zones. So your blue part are the larger volcanic zones, okay. The red part are the small volcanic zones. And then this yellow part, if you all can see, these are the places which are of a very high earthquake, okay, a region of very high earthquake. Now just check on here, this is India and this is where we live. This is North Bengal, okay. This is, see, just check on here if you all can zoom. So even in the Himalayas are the very high earthquake prone areas, okay. And nobody knows because it's kind of like a separating from the Eurasian plate, our India, okay. Previously it met and mixed with each other and formed the Himalayas. Now it is separating. And this is something of a great study. And then we come, after all this, we come to the theory that we all believe in now. Okay, not the continental plate theory, but the plate tectonics theory. So there were these three people, Mukherjee, Parker, and Morgan. Okay, he said that the lithosphere consists of crust and upper mantle. Okay, but the crust and the upper mantle, but their movement is not on the continental parts only. He said, it's not that only the continents move. Okay, just like here in the continental drift theory that we did, it said that only the continents moved. See, the ocean stayed static. But in plate tectonic theory, it said that it's not that only the continents moved, but there are some major plates inside the interior, okay, inside the comprising of the crust and the upper mantle, major plates inside the continents or inside the oceanic floor. Okay, seven major plates and then some minor plates. Okay, these plates move as a whole, whether it is an ocean or whether it is a continent. So continental drift theory and plate tectonic theory has this only simple difference. Continental drift theory states that only the continents move apart from each other or towards each other. Now the plate tectonic theory suggests that not just a continent but even the oceanic floor moves, okay, because even the ocean has plates inside them. So these are the plates division, okay, and this is highly accepted now. Okay, so plates comprise of what? Land and oceanic floor as well. Okay, so that's all. That's very simple. Now the forces. Okay, now the mechanism. How can the two plates they meet or be apart from each other? What are the mechanisms? So one is the transform boundaries. Okay, they slide from each other. Okay, there are two plates and one slides towards the left and the others towards the right. They slide from each other. This is known as a transform boundary. The other is the divergent boundary. It's like faulting, right? So when two plates they move apart from each other, there is a depression. Okay, there is a depression created. That you can see in the mid-Atlantic Ocean as well, between the American and the Eurasian plates. Okay, you can go and experience this someday. Okay, mid-Atlantic ridge. So and then these are the two, and one is the convergence. Now convergence is like folding. Okay, when two of the continental plates they meet, they fold and they form some kind of a mountain. Okay, so that's all. It's very simple. And then the weight, then other thing is, how do we know about the plate tectonic movement? Is there was a study once, and there was something called a gryphometer. Now it's a very simple device. They used to place some kind of a wire, okay, and wire, and they used to attach it in on the tip used to be like attached to some device, okay, not a very high device. It used to be a very simple instrument. Now the wire was stretchable, okay, and they left it for a year. After a year, they came and they measured the wire. Now the wire had been stretched. That means what? The plates were moving apart from each other. Okay, and then they measured it, and it was not high. It was 5 to 10 millimeter per year. So that's how our plates move apart from each other, 5 to 10 millimeter per year. So that instrument is called Grigometer. Okay, and the forces here needed is the convectional force. So convectional you all know, right? And convection of what? Convection of magma. Okay, so the magma comes out, moves to a certain distance, cools down. Okay, so that's how the circle it keeps on doing a circle, and that's how there is a convectional force. Okay, and that's what makes the plates move from each other. So this all is a revision. Okay, now download Google Form. Okay, and the app name is Google Form. Download that. Next class we'll have a short test on these 4 chapters. Okay, then take care.